We're going to talk about gases now. We've talked about some thermodynamics effects that we see with solids and liquids and changing states. But when we start to talk about gases, and specifically ideal gases, and what we mean by ideal gases are that when they interact, they bounce off of each other, they don't stick together. The only forces they experience is we think of them as billiard balls. So this model works really well for ideal gases and molecules. Works really well. Yes, it works very well for ideal gases. It works for noble gases, but other molecules can be approximated often as these billiard ball type models unless the pressure is too high. And the reason we really focus on this is where we can start to make the connection between thermodynamic quantities and quantities that we've already learned about from Physics 1. So to remind you, we have an ideal gas, and you know the ideal gas equation is pressure times volume, and you probably learned it as nRT, where N is the number of moles and R is an ideal gas constant, and they're different units you can give R in. In physics, we'll often write this as PV equals capital N kBT, where this is now number of particles, because it's just easier for us to think in terms of particles than moles, at least when we're setting this up. And this K sub B is Boltzmann's constant. So KB is Boltzmann's constant, and it's given by 1.23 times 10 to the minus 23rd. And then the units of this, because pressure times volume, it turns out this has units of work. We'll see that in a minute. So that's going to be joules, and this is going to be per Kelvin, and we assume that we know that we're in number of particles. Now we can connect these two by recognizing, okay, little n times big R is equal to this, and so the connection is actually, and I need to look at notes here, is that R is equal to Avogadro's number times KB, and you probably know R as probably 0.821. This is in liters per atmosphere over moles Kelvin. And liters per atmosphere is kind of a version of work, but it's not in joules. So if we want to get into joules, this becomes 8.31 joules per mole Kelvin, and then you may have also seen it as 1.99 calories per mole Kelvin. This is an instance where, because we're not taking the difference in temperature, we really do need to stick with the absolute temperature scale. Okay, so these are our units. When we want to calculate joules, we want to do it use this term when we're looking at it in physics. Okay, so let me make the case that pressure times volume is actually a unit of work. So the units of pressure, remember pressure is force over area, and then volume, so pressure times volume would just be force over area times a volume. Well, a volume is, if it's a square, if it's a cube, that would be a length cubed, and area would be a length squared. So this would have units of then newtons, sorry, it's not force, it's really force over area. So I'm looking at units of this would be newtons over meters squared times meters cubed, which is a newton meter, which is in fact a joule. Okay, so one other thing, so this has units of energy work, right? One other thing to say, we're going to often plot this as pressure versus volume, which may or may not be a way you're used to seeing this. You can plot it pressure versus temperature at a constant volume, but if we have a constant temperature, then that means we've got pressure is equal to some constant constant times 1 over the volume, which gives me something that looks like this, right? When the volume gets big, this gets small, and when the volume gets small, this pressure gets big. And so this would be at one constant number 1, and then you can get another curve associated for constant number 2. And so this is actually a higher temperature than this. So this would be at a T1 and a T2, where your temperature 2 is greater than temperature 1, okay, because this constant would be bigger, which shifts the curve out a little bit, okay? And these are what are called isotherms, or constant temperature curves, right here. And so we're going to see those as we go along. But this is really just one way to describe how pressure varies with volume. So if we change the volume of something and we hold its temperature fixed, so we have to be careful about what we're doing, then this is the kind of curve that we have. If we're just squeezing something down, like with a bicycle pump, and we're pushing the air out, we're not necessarily holding the temperature fixed. So we really have to pay attention to what is it that we're holding fixed. Are we holding pressure fixed, volume fixed, or temperatures fixed? And you're probably used to hearing about this in chemistry with like Boyle's law, Charles's law, Gay-Lussac's law, all of those. But they're all really encoded in this expression. So if we can hold on to this expression and realize it's possible for pressure, volume, number of moles or number of particles, and temperature to change, then that's something that we need to hold on to. It's not necessarily that every time you change your pressure, you decrease your pressure, your temperature, your volume has to go up. That isn't necessarily the case. It depends on what's happening over here. Okay. The other warning I want to give you, you probably know this as well from chemistry, is that this temperature needs to be an absolute temperature, right? If we talk about a doubling in temperature, 20 Celsius to 40 Celsius is not a doubling in temperature. Neither is 50 degrees Fahrenheit to 100 degrees Fahrenheit, because those are not absolute scales. So if we're looking at about 300 Kelvin, then to double that, we're talking 600 Kelvin. Okay, that's a true doubling of temperature. And we're going to see why in just a minute. What I want to do now is make the case to that connects the temperature, pressure, volume to what's happening at a microscopic level, right? Pressure, volume, and temperature are all macroscopic. They're big picture measurements. But what we want to do is connect it to what's going on sort of at the atoms or molecules bouncing around. And so I want to look at what causes the pressure. If you have a gas in a container, what causes the pressure is the particles going and hitting that wall. So going and hitting the wall and bouncing off. Okay, so here's my wall. Here's a left side of a box. We'll build the box in a minute. And we're going to just look at one particle going in and coming back out. So if I have a particle comes in and goes back out like this, then we can look at the change in momentum, right? And the change in momentum, if it bounces in and comes back out, if it's an elastic collision here, then we can say that our momentum in the y is not changed because there's no forces happening in the y direction. And so what happens is this change in momentum that we have, I'm going to use a script P for our momentum because I've got a P for pressure. This is where all of our letters sort of get on top of each other, is going to be my mass times my v in the x direction. This is my x direction, right? X. Or my I hat direction. And here, this is Vx of that, and this is going to be my Vx going in. So you can see that it changed. The y parts don't change. My Vx coming out, so that would be in the positive I hat direction, minus mVx in the minus I hat direction, because it's coming in the minus I hat direction. And so this gives me a change in momentum of this particle of 2m x in the I hat direction. Okay, so this change in momentum is provided by the force from the wall. So the wall provides a force like this. This is the wall's force, a normal force if you like, force from wall, force that would be from the wall, which means the gas provides a force on the wall in this direction. So that's the force on the wall, and that's going to contribute to the pressure, right? So the magnitude of this force on the wall, which will be to the left in the minus I hat direction, and this magnitude of this force due to this one particle is going to be equal to this delta change in momentum, right, over whatever time interval that happens. Okay, so my magnitude then, F1, I'm gonna get rid of the vectors, is going to be equal to 2 Vx over delta t. Okay, so delta t would be the time over which, well, the average force is really what we're looking at, right, on the wall. Not just this collision time. That would be my peak force, and it would be peaked at that point. You'd have a nice high force however long this collision took. But if we want sort of an average force, which is really what we're looking at here, this is a time average force, an average force, then we need to know the time between collisions. And so if we look at this, that bounces off, and then we say, well, okay, so if we're looking the time it takes to bounce, then this particle comes in, comes back out, hits the other side, right? Here's the other wall, right? Hits that, comes back out, and eventually hits this wall again. And if these walls are separated by a distance L, then we can say, oh, well, if we know how fast it's going in the x direction, that's going to tell us how long it takes to get through L. The only thing that changes its speed is when if it's the only particle in the box, is when it hits this wall. So if we look at that, we can say we can just use our kinematics equations back from the first week of Physics 1 and say that this distance is equal to whatever our velocity is in the x direction times the time it takes to make one to go across here, right? That would be the time to go this distance L. And so this delta t is going to be 2 of these. So delta L, because we have to go, we have to start here, go across, and then comes back. So delta t is going to equal 2L over Vx. And the reason we can use this expression instead of our usual x equals x naught plus v naught t plus 1/2 a t squared is, of course, this acceleration is 0. There's nothing accelerating it left or right, and we can just say that we started at 0. So that's where that equation comes from. So if I plug that into here, then I'm going to have F for one particle is equal to 2m Vx over this delta t, which is now going to be 2L divided by Vx. Okay, the 2's are going to cancel, and this is going to look like m. Because I've got something in the denominator, I have to flip it over. M Vx squared over L. So that's the force if I have one particle that's bouncing around. Well, of course, we don't just have one particle in a box. We have many. And so what we do is we say if we have n particles, so n number of particles here, then we would say the total force would be this sum from I equals 1 to n of F sub I. In other words, I have to add up all of these. So this becomes the sum of 1, in other words, it would be F1 plus F2 plus F3. So that would be m. If it's all the same particle, which I didn't say it was, but we're going to say it's all the same mass, Vx I squared, because all the particles could have different initial speeds, and in fact, they don't all have the same speed, over L. Okay, so what we need to do is add up all of these x velocity squared for all of the different particles. So there's one particle in here, but there could be a second particle that doesn't quite go as fast, and it hits the wall and bounces and comes along. Okay? So M and L are constants. They can come out of this sum. But this is kind of a messy sum, Vxi squared from 1 to n. But really, we don't care about the individual speed of any one particular particle. We're really going to be more interested in sort of the average speed. That's a good way to sort of get at what's happening in aggregate behavior. So if you remember, to find an average, you probably know this, to find the average of your grades, you add up all your grades if they're all weighted the same. You add up all your grades, your 80s, your 70s, your 99s, your 95s, by however many grades there are. So an average is adding up all of whatever it is over how many you have. That gives you what we call the average value of x, and we denote it with a bar often. So I can do the same thing. I can look at then the average value of Vx squared. That would be the average speed associated with the x motion, is equal to then the sum from n equals 1 to n, from I equals 1 to n, in other words, all of them possibly adding up together, Vxi n squared, all divided by n, right? So where I have this, I can multiply both sides by n. I can have an n over here and an n over here, and that just cancels. We're not adding. I mean, n doesn't depend on, there's not like different numbers of particles or anything. So what I can do is, in place of this nasty sum, I can just put this in place. So I'm going to do that and rewrite my force is equal to m over L n times Vx squared, the average value of the speed in the x direction squared. Okay, so that's fine. Really though, particles can move in the x, y, and z direction. And so we can say, of course, that you probably, maybe you remember from Physics 1, that when we had a vector like this, our velocity vector, we had x, Vx, and Vy. That looks vaguely familiar, and we could use a Pythagorean relationship that said v squared, the magnitude of this squared, equals Vx squared plus Vy squared. And in 3 dimensions, this becomes plus Vz squared. And so if particles are just as likely to be going in the x direction, the y direction, and the z direction, we can claim that average Vx squared is going to be essentially equal to the average value, because we're talking average values, and the particles probably don't care what direction is up, right? We're just an arbitrary direction. These are all equal to about the same thing. So I could say my average speed squared would be Vx, average Vx squared plus average Vy squared plus average Vz squared, but these would all be the same. So this is essentially equal to 3 Vx squared. Okay, yes, we're doing averages, and that's okay. The reason averages are okay is because we're not looking at 1 or 2 particles. We're looking at Avogadro's number worth of particles, which is a lot of particles. So in place of a Vx squared, I'm going to, I guess I should rewrite this a little bit. I'm going to say then the average V squared is equal to 3 Vx squared. That's just pulling this is equal to this. And so in place of Vx squared up here in my force, I'm going to put in a 1/3 average V squared. So I'm going to say that my force is then equal to m over L n times 1/3 my average speed squared. Okay, I'm almost there. It doesn't look like it, but I can get to pressure from force. So this is my force. It depends on the number of particles. That's not a surprise. More particles, more opportunities to hit. The mass, that's not a surprise. This length comes from how long it takes to get back and forth. If you have a really big box, that'll matter. And then how fast I'm going. Okay, so all of these things make sense. And in fact, this how fast I'm going, we're going to connect to, not surprisingly, kinetic energy. So this force we can get to pressure from. So we can say that pressure, right? Oh, that was on the previous screen. Pressure is equal to force over area, right? So force over area. So let's take this expression, right, and divide for force and say pressure is equal to this divided by area, or M over L times the area, 1/3 average of V squared, not V sub 2. Okay, this length times average, well, that's not average, sorry, length times area, that's the area here, right, the surface area. So length times surface area is the volume. Okay, so we've got our pressure is force over area, pressure is mass, L over area, and then I've got to have an N. I can't just drop that out, number of particles, right? That's important for the pressure. Okay, so, but I'm going to use this to say, if I take this, which we can recognize as our volume, right? Length times the cross-sectional area is our volume. Multiply that over here, I get pressure times volume is equal to 1/3 mv squared times n. And so if we look at this and use this expression right here, then PV equals that, then I can put in N kVt is equal to 1/3 mv squared times n. The n's cancel. If I multiply by a 2 over 2, so I get a 1/2, and I'm going to put the 2 over here, this we can recognize as average kinetic energy. So my average kinetic energy per particle sort of average value is going to be 3/2 kBt. So our temperature, which we first talked about as just what our thermometer measures, is actually a measurement of the kinetic energy of a particle. So the average kinetic energy for a particle. If we have a lot of them and they're all moving around, then we can talk about our average. Our internal energy is just being the number of particles times K times our average kinetic energy, because that's the energy we have. You think about bouncing BBs or something like that, then this becomes 3/2 in kBt. That is our average internal energy. If we want to find our average speed, obviously we can go back here and find it that way. So you can have expressions that look like your, this is called your RMS speed, but basically the square root of your average speed squared is equal to square root of 3 kBt over m. You can see it like that. Sometimes you can see it in terms of r, so you can substitute this in place for r over n to get it in terms of molar mass. But this gives you what's called, yeah, that's going to not show up on the screen. That's called your RMS speed. Root means square. It just means you're taking the square root of an average. It's a way of getting at an average speed. So if you know the temperature in a room, say it's 300 Kelvin, you put these values in, you know the mass of the molecule or atom that is the predominant gas, then you can find out its average speed. And so then you can get an idea of really how fast are the gases in this room moving. You're getting hit by some pretty speedy molecules and atoms. but they're so light you don't feel it. You're used to that kind of bombardment all the time.